Okay, I want to go over a proof, an example proof involving sets. So this is going to be a proof where we show an if and only if statement. So I'm going to show you how to prove an if and only if. And then also, this is going to be a proof in which we show that two sets are equal to each other. So we're going to use the definition of the equality of sets to prove that. So let's look at the statement. The statement is, prove that for any two sets A and B, the power set of A is equal to the power set of B if and only if A equals B. So remember, the power set of a set is the set that consists of all subsets of that set. So the power set of A is a new set you make that has as its elements all the subsets of A, okay, all the possible subsets. And then that would be the same for B. So the way we're going to prove an if and only if, remember if and only if refers to the biconditional statement. And biconditional is equivalent to like one direction and the other direction, right? Implication one way and implication the other way. And so the best way to prove biconditional is to prove each implication direction separately, right? So our proof will begin by proving one direction or the other. So with this as our sort of left side, right? And this is our right side over here. I'm going to start with left side, proving that the left side implies the right side. So at the beginning, the first part of my proof is going to be the right direction. So that means we'll start, I'm going to prove this directly, okay, with a direct proof. So I'm going to start by assuming the left side here. I'm going to assume, for sets A and B, I'm going to assume the power set of A is equal to the power set of B. Now, what we want to do here, I'm just going to parenthetically say we want to show that A equals B. So in order to do this, what we want to do is show A is a subset of B and B is a subset of A. So what we're going to do is prove that one of these sets is a subset of the other. And now, it occurs to me that there's some symmetry in this problem, right? If I can show that A is a subset of B, well, is there really any distinction between A and B? Is there anything about A and B that's different? If I were to say, for example, swap A and B here, power set of B equals power set of A, isn't that just the exact same statement? If I swap the names of these sets A and B, aren't I talking about the exact same thing? This is a perfect situation to use without loss of generality. So I'm going to say Wolog, we will show A is a subset of B. This will ensure B is also a subset of A by symmetry, essentially. So A will equal B. Okay. When you're proving something, it sometimes is useful to state what you're going to do, because then it says to the reader, here's where we're going with this. Follow me along. Okay, so without loss of generality, we're going to show that A is a subset of B, and this will also show that B is a subset of A, and so A will equal B. All right, that's our goal. So now, I want to show this. A is a subset of B. Okay, in order to do that, I'm going to use the definition. The definition of being a subset is that any element which is in A must therefore also be in B. So actually what I can do is I can start with an element and assume that it's in A, and then use my assumption about the power sets here to somehow argue that that element must also be in B. All right? So I'm going to do this very general. I'm not going to specify any elements. In fact, I know nothing about these sets. So I don't even have any elements to specify, right? I don't know whether the elements of these sets are numbers, or whether they're people, or whether they're colors, or like graphs, or functions. They could be all kinds of different things. I'm just going to say, let X be an element of A, okay? And that's going to be arbitrary. If you don't include the words, let X be arbitrary, it's generally implied that it's arbitrary, but it's nice to be explicit about things. So let X be this is saying let X be an element of A, let that be arbitrary. So we have an arbitrary X. Now then, here's what I can do. I know that any subset of A is an element of the power set, and I know that the power set equals the power set of B, right? So all I need to do is find an element of the power set, and then I'll be able to use this equality to kind of cross over into talking about the set B instead of the set A. So how can I make an element of the power set? Well, one way to do that is to make a singleton. I have this arbitrary element of X. I want to show that it must be an element of B. I misspoke there. Sorry, I have this X, which is an arbitrary element of A. I want to show that it's an element of B. So let's take this singleton, like that. See? I'm going to put X in a singleton. Then that is an element of, sorry, let me put it this way. That is a subset of the set A, right? So it is an element of the power set of A. Okay? Since, by assumption, the power set of A and the power set of B are equal to each other, an element of the power set of A, an element is in the power set of A if and only if it's in the power set of B. So since that's the case, we can now say this singleton containing X is also an element of the power set of B. So if the singleton containing X is an element of the power set, it means that it's a subset. The singleton containing X is a subset of B, right? Because that's exactly what the power set is. It is the set of all subsets, right? So this singleton is now a subset of B. All right, I'm getting close. If that's a subset of B, then it means that any element which is in this set is also in B. That's the definition of a subset, right? So I can finish by saying, thus, X is an element of B. Okay, now this was arbitrary, right? Now what I'm going to do is I'm actually going to do a universal generalization now. Okay, you don't necessarily need to cite these rules of inference when you use them. Most proofs will glaze over that. But what we are doing here is a universal generalization, because we can say now, for all X, if X is an element of A, then, I don't know why I put a parenthesis there. Sorry, ignore that parenthesis. It's just, my hand sometimes does things it's not, I don't want it to do. X is an element of A. If that's true, then X is an element of B. Because I just proved with this arbitrary element, if it's in A, then it's in B. So it's true for all, right? That is a generalization. You can only do that because the element was arbitrary and therefore could have been any element, all right? That's why this word is so important. So now that's true, and that is the definition of A is a subset of B. Okay. Now we said without loss of generality, we will show that A is a subset of B. Okay. Now, so that means similarly, B is a subset of A. Because remember, the argument for B as a subset of A is going to look identical to this, except you swap all the A's and B's around, right? Because of that symmetry involved. So, by the same argument, that's true. And then therefore, A equals B, because they're subsets of each other, right? That's what this gives me. I'm just going to highlight these here. A is a subset of B, B is a subset of A, therefore they're equal. All right, so we just proved the forward direction. We proved that if the power sets are equal, then the sets must have been equal. So that completes half the proof. The second half of the proof would start something like assume A equals B. Now, when you begin the second half of the proof, you're completely starting over, right? You're saying, okay, wipe the slate clean. We're going to start over and forget all the stuff we had assumed before. We're now going to assume A equals B, and then work from there and try to prove that the power set of A equals the power set of B. Okay, so you now want to show power set of A equals power set of B. Now, I'm not going to go through the rest of the proof. I'm actually going to leave this as an exercise for you to do on your own. Okay? So I've shown you how to do one direction. Now you can do the other direction. It's somewhat similar. It uses all the same ideas. It's not going to be identical because you're kind of, instead of going from power set down to set, you're going from set back up to power set. But, you're going to use a lot of the same kind of steps. Yeah, give that a try. And if you have any questions, let me know.